Hello, everybody. My name is Juan, and I'm going to present our paper Unsupervised Representation Learning by Predicting Random Distances. My name is Juan, and the author group includes Juan, Guansong Pan, Chunghua Shen, and Chongbo Ma. We are from the University of Adelaide. So what exactly we have done is deep neural networks are a set of data-driven approaches which have gained tremendous success in broad range of machine learning tasks because it has had a strong capability to learn semantic-rich features from high-dimensional data. But they often requires large-scale label data to successfully learn these features because data is important for data-driven approaches. But this significantly hinders their adaptation into unsupervised learning tasks. And in some domains, in some tasks, the label data is very expensive to get. So in order to enable unsupervised learning on those domains, in this work, we propose to learn features without label data by training neural networks to predict data distance in a randomly projected space. Random mapping is a theoretically proven approach, so it has a strong theoretical background. And to well predict these random distances, the representation learner is optimized to learn genuine class structures that are implicitly embedded in the random projected space. And empirically, we test our methods on 19 real-world data sets that receive good results and shows the effectiveness of methods. And the code is available here at this address. So in the random distance prediction RDP methods, the key intuition is that given some distance information that are truthfully encapsulates the underlying class structure in the data, the representation learner is forced to learn the class structure in order to yield distance that are close as the given distances. So more specifically, given data, a pair of data points, xi and j belongs to dimension d, we first fit into a shared weighted semisis style neural network phi with a parameter theta, and theta projects the dimension d to the dimension m. Something like this, we calculate the distance between, or calculate differences between the distance predicted by phi and the predicted by predefined function eta. In this work, we used inner product to calculate the distance similarity because it's very efficient, and we use the MSE as our objective function. So the equation 2 is our final objective function here. So in the previous slides, what we have talked can be encapsulated into this figure. We can see that a pair of points xi and j are first fit into a neural network, a shared with neural networks phi with a parameter theta, and then predicted the distances predicted by theta, the phi, and then we also repeat this process and predict the distance given eta, which is a predefined distances. And then we try to minimize the loss RDP by minimize this loss function. The difference between the distances predicted by phi and predicted by eta. So in this figure, it's worth noting that the lower right figure represents the 2D t-SNE visualization of the feature learned by RDP on a small toy dataset, OPT digits, with 10 classes. You can see here, individual classes are separated with each other quite well using our methods. So it also shows the effectiveness of our proposed RDP methods. And the performance evaluation in anomaly detection tasks, the table 1 shows on 14 data sets with those comparing methods. You can see that in most cases, our RDP methods receives substantially better performance than the other methods. And similarly, in the clustering tasks, in both NMI performance and F-score performance, when comparing to different comparing methods, our RDP can receive significantly better methods than results in the other methods as well. So it generally shows the effectiveness of our proposed methods. Thank you. I think that's it for today. Thank you for your time and your listening.